Hey there, in this video we're going to start off by going over all the functions and doing a comprehensive review of functions we may have learned in pre-calculus before we get into the nitty-gritty in chapter 2 of calculus concepts. So first of all, what is a function? A function is a rule that assigns to each value in the domain exactly one value in the range. And so this is pretty important that it is exactly one value in the range. So we have a function, the domain here is in pink, and then the range is in blue. And notice also there are different shapes to indicate that the domain and the range don't have to be the same when you have a function. So you have values in the domain, you have the function, the rule, and then they assign exactly one value in the range. So in this case, notice that A and B are different. They do go to the same value, so f of A and f of B may go to the same thing. So that would be as if when you're working with a parabola. If we have a parabola like y equals x squared, for example, notice that every x goes to exactly one y value. So when you have the y value of 4 here, right, this is the same value that 2 and -2 go to, but it is -2 goes to only 4 and 2 also goes to only 4. So that's like the instance here of A and B. So A and B are different, just like 2 and -2 are different here, but both -2 and 2 go to the same value 4. Here A and B go to the same value. F of A equals F of B. So that's kind of what that means. Another way that we can think of when something is a function that every value in the domain goes to exactly one value in the range is by doing the vertical line test, right? If we draw a vertical line anywhere on the graph of a function, it touches only once. So that is another way that tells that something is a function. And so now an example here, let f of x be 2x minus 3. So one of the things we want to know is what is the domain of that function. And so we can start by plugging in values and see, can we plug in any value? So can I plug in f of -5? And so if I put that in, I'm going to have 2 times -5 minus 3, right? So that's what, -10 minus 3, so -13. So I was able to get a y value. And then f of 2, so 2 times 2 minus 3, so that's 4 minus 3, which is 1. So we're able to, so I know that then 2 and -5 are in the domain. And this is already written as a rule that it is a function. As soon as you see the notation f of x or g of x or h of x, that means that that is already a function. But the main thing is, right, can I pick any x and get exactly just one value of y? And in this case, we will. The graph of y equals 2x minus 3 is a line, and a line passes the vertical line test. So that one will be a function. Since I already talked about the vertical line test, let's look at our next example. So use the vertical line test to identify graphs in which y is a function of x. So are these functions? Do they pass the vertical line test? Meaning, if I draw a line anywhere in here, do they touch only once? Right? So if you move this line anywhere along the graph of A, notice that that is going to touch only once. So then we can say yes, function. What about B? Well, if I draw a line on top of the graph of B, it's going to touch infinitely many times because it's just going to go on top of that blue line. So we can say this is no, not a function. Because whatever that x value is, that means it has infinitely many y values. And to be a function, every x value has to have exactly one value. What about C? Is it a function? If you draw a vertical line anywhere on it, do you touch only once? No, right? You're gonna touch multiple times. Same with D. So the only one that is a function in here happens to be A. And so these are not functions. My lines are not very straight here. They don't pass the vertical line test. So when you draw a vertical line on a graph, it has to touch only once, just like in here. If you draw a vertical line anywhere in here, it's going to touch the graph of the rule only once. Let's go to our next example. When we have the graph, it's pretty easy to tell whether it's going to be a function or not because we can draw the vertical line. But what if we just have the rules for the equation, for the rules? So in this case, let's look at these functions. Determine whether the relations are functions or not. Now let's keep in mind our definition. The definition of a function is that for every x, so every element of the domain goes to exactly one value in the range. So essentially, can we write y as a function of x? So the big question we want to know for all of these is, can we say y equals f of x? So can you solve for y and just get a single expression? So for part A, let's copy that and solve for y. So when I have this equation and I try to solve for y, so I'm going to have then y squared equals 16 minus 2x, right? Subtract x from both sides. And now notice that I'm going to have to take the square root of both sides here to get y by itself. And what happens anytime you take the square root of something? We gain a plus or minus, right? So this is going to be plus or minus the square root of 16 minus 2x. So is this a function or no? No, right? So then this is going to be not a function. Why not? Well, because for any x that I put in, I'm going to have y equals plus or minus whatever that x value is. So if I put in 1, right, then this is, if x is 1, you're going to have y equals plus or minus the square root of 16 minus 2 times 1, so plus or minus the square root of 14. So you get, for every x, you're going to get 2 y values. So think about that graphically. If you were going to plot it, right, at x equals 1, you have to put a dot at the square root of 14, and then a dot at the square root of, or negative the square root of 14. So that will make it so that it doesn't pass the vertical line test. So this is not a function. So let's highlight that. So this is not a function. What about b? Is b a function? So let's do the same thing. Let's copy it and try to solve for y. So can I write y as a function of x? So that's the big question when you're doing things algebraically. Here, to solve for y, what do I have to do? We have to square both sides to get rid of the square. So we go square, so I get y equals x squared plus 1 squared. And that seems okay. If I plug in any x, do I get this issue here? I don't have a plus or minus, right? I'm just going to square it. In fact, everything is going to be positive, because if you take any x, do stuff to it, square it, everything is going to be positive. So there are going to be no repeat values here. So we can say that, yes, this is a function. And what about c? Is c a function? Y equals cosine of x. Does it pass the vertical line test? If you think of the graph of cosine, depending how long it's been since you've had your trig, we can think of the graph of cosine and we can try to think, does that pass the vertical line test? And algebraically, cosine it gives you values between 0 and 2 pi, and then it just repeats along to infinity, but the y values never repeat. So this one's a little bit harder to show algebraically, but it is a function. It's already also solved for y equals cosine of x, so we can easily say here f of x equals cosine of x. And so this is a function. Once we know that our rule that we have is a function, then we're interested in doing a lot more with that function. And some of the things that we want to know always is what is the domain? What are the x values that I can use for that function? And then what is the range is another one. We always tend to focus on the domain because that's what is giving us the inputs. So what can I put into a function? And so in this case, let's try example 4. Let f of x be that rational function and g of x be this radical function. So there are some things that we have to remember about just fractions and then radicals, especially in this case, square roots. So what, looking at f of x, what is it that you can't do when you have a fraction? We can't divide by 0, right? So when you have a fraction, a rational function, we want to make sure that the denominator cannot be 0. So we don't want the denominator to be 0. So that means, because otherwise we're going to have undefined. So if the denominator is 0, that means the function is undefined, which means then any x value that makes the denominator 0 is not going to be on the domain. So this, the denominator, is 0 when x equals 2, right? So that means that when x is 2, f of 2 is undefined, right? So if you try to put it in, right, you're going to have 2 plus 1 equals 2 minus 2. You're going to have 3 over 0, which is not possible. So in that case, we say x equals 2 is not in the domain of the function. Is there anything else that is not in the domain? Only the things that are not in the domain are things that make the function undefined. That's the only thing that makes the function undefined. So then we can say that the domain is all real numbers except 2. But we're going to write that in interval notation. So the domain is going to be minus infinity to 2, and we don't want to include it, so parentheses, and then or, the union for or, 2 all the way to infinity. So this is saying everything except 2. Visually, if you're a visual person like me that likes to see it in a graph form, that means that we're going to have 2. If I put a circle on 2, I'm not going to shade it in because it's not included, but I get to shade in everything else. So that is, so then from the number line, I can translate to the interval notation. In this class, most of the time we're going to be, in calculus in general, we write domains and range in interval notation. Occasionally, you'll see the set builder notation. And so set builder notation uses the braces. So as you have x such that x is not equal to 2. And so this will be your set D, the domain. What about for our g of x function? G of x is a radical function. So here we have to remember what are some things that we know about radicals, especially square roots. Any even root, what is the one thing you can't do with square roots? We cannot take the square root of a negative number, right? So we can't take the square root of a negative number. So what does that mean? We can't take the square root of a negative number. That means that whatever x is can't make the inside negative. Now, that doesn't mean that x can't be negative. It just means that the inside of the radical can't be negative. So that means in this case, what we want the inside of the radical. So we want x plus 2 to be greater than or equal to 0. Equal because what is the square root of 0? Square root of 0 is 0. So that one is okay. And then the square root of a positive number is defined, whereas the square root of a negative number is not defined. It's imaginary. So we want x plus 2 to be 0 or positive number. So we want it to be x plus 2 to be greater or equal to 0, solve for x. So x is greater or equal to negative 2. And so this will be our domain. So how do you write that? In set builder notation, we can say D is X such that X is greater than or equal to minus 2. Some people like set builder notation because it's really just your answer to that inequality. And in interval notation, we will say, well, X has to be greater than or equal to. So it can't be negative, and beyond that, beyond -2. So I'm going to have -2, and it is included, right? It is equal, so parentheses or bracket. Yes, we're going to use bracket. I'm just going to assume that you said bracket. -2 all the way to where? X has to be greater or equal to -2, and that's the only restriction we have. So all the way to infinity. And so that is our interval notation. If you have a hard time going from the inequality to the interval notation, you can write yourself an intermediate step of the number line. I put -2 in there, solid because we're including it, and then shade everything up. All right, so I'll record another video with more examples.